Okay,
Yeah,
hello
go ahead.
everyone.
Please.
So today our first speaker is Praneet Nandan from ESPCI Paris, and he will talk to us about diluted autocatalytic course classification and monostationarity. So Praneet, please take it away.
Hmm. Thank you. Thank you, first of all, for inviting me for this seminar series. It's really nice to talk with everyone about things we all are interested in. Today, I'm going to talk about the diluted autocatalytic course, and the talk will be based on one of our recent preprints. Like the preprint has been on the archive for a while, and the paper is also in the final stages of review, so should appear in a journal soon. This is an article by me and my two supervisors, Philip and Jeremy. And what we mainly talk about in this paper is an investigation into autocatalytic course, but in a specific regime, which is the diluted regime. So I'll start with, oh, you see, yes. So there will be two broad sections of the talk. One will be talking about the introduction and what are the diluted autocatalytic cores and their classification. And the second part, which is like the more bulk of the paper, is about the uniqueness of the stationary states of these cores. So first of all, to start, let me talk about one of these papers, which appeared in 2020. It's by Alex, David, and Philip. Two of them are in the meeting now. And it was about stoichiometric autocatalysis and about the classification of the different types of cores that can appear in stoichiometric autocatalysis. First of all, the stoichiometric autocatalysis was defined as autonomous. What autonomous means that if you have any reaction, it must have a reactant and a product. Autonomity condition is important in this context because when you look at the submatrix of the stoichiometric matrix, it might happen that you leave out some reactant or some product and you have a reaction which just appears out of nothing or goes into nothing, which makes sense for a system having degradation or inflow. But this was a restriction imposed to have a reactant and a product for each reaction. And then non-ambiguity means that there should not be the same species on both sides of the reaction as a reactant and as a product. What this implies is that for any reaction which has a catalyst and it's like A plus B gives 2B or something like this, then you need to have an intermediate complex which is made by the reactants and then it breaks into the species, which will then satisfy the non-ambiguity condition. So if you have a reaction network which is autonomous and unambiguous, then it is stoichiometrically autocatalytic if there is a positive column vector which gives a strictly positive right. So it's the image space of the stoichiometric matrix, and the column vector is nothing but a reaction vector. So how many instances of each reaction you can have? So there must exist some combination of reactions which gives every species number to increase on the application of these reactions. Then, given this condition for stoichiometric autocatalysis, we can define autocatalytic cores, which an autocatalytic motif is a sub matrix. It's a sub network of a network which satisfies this condition. And then a core further is a motif which is minimal. So you cannot find anything smaller than this core, which also satisfies this condition. Anything you remove will break one of the conditions for being stoichiometrically autocatalytic. And in the paper, the classification found there are five different types of cores, the structure of the cores which are possible, which were type 1 to type 5. Then moving further, what we would focus on is dynamic autocatalysis instead of stoichiometric one. So the stoichiometric autocatalysis, by definition, gives a condition which will give that the stoichiometric number of the species increases on the application. So it's a system in which you can have a cycle of reactions which gives an increase in number for each species. But what dynamical autocatalysis implies is that there is a growth in the concentration of each species. So it would have a Lyapunov exponent and a direction, which is the eigenvector, in which it will grow exponentially fast, which is kind of implementing a kinetic condition as well. So a small note is that here it is defined for mass action system, and throughout the paper we work with mass action. But later on, I think generalization to other mechanisms are also possible. But just as a simplest base case, we take mass action because things can be broken down into mass action terms. Then, given this definition of dynamic autocatalysis, we would want to investigate things in a specific regime, which we call here as the diluted regime. What we mean in a diluted regime is all the concentration of species is very low. Why we pick this specific regime is because the main, like the shine of autocatalysis is that it can increase the concentration of something very like exponentially. So in the diluted regime, when everything is very small, autocatalysis can help certain species, certain systems to grow much more than the neighboring species and create a specific imbalance in the species, which is where the autocatalytic cycles and competition and these kinds of notions become important. But more mathematically, what we mean by diluted reaction network is that it is a diluted network if it contains only one or one-to-many reactions. So all the reactions will be either of these three forms. It's single reactant and single product going to each other irreversibly, going to each other reversibly, or it's a single reactant giving an array of products, but it's a irreversible unidirectional reaction. These conditions correspond to diluted regime because when we have very low concentration, we assume that under mass action, there's such low chances of two species meeting that any reaction which has two reactant is or will take too long to happen, and that will be beyond the scope of the time regime that we are looking at. And just imposing this dilute regime, we get two differences from the formalism of this paper for the stoichiometric autocatalysis. One of them is that there's a restriction on the stoichiometry of the species. So all the reactants have only a single reactant. So the stoichiometry of the reactant is one. We cannot even have 2x giving x prime because that breaks the rule of the diluted regime. While in the paper for the stoichiometric autocatalysis, it was allowed to have higher stoichiometry. It could be 5a giving 6b, and it would be there in the matrix because it's a metric condition, so it's fine. And the other difference is the inclusion of irreversible reactions. In the paper, all the reactions were reversible, but here there will be some reactions which are in a single direction. It's either moving forward or moving. There are irreversible ones included, but there are also reversible ones. Then moving forward, we describe for such a system. So this example is three reactions, xi giving xj plus xk, xi reversibly going to xl, and xk reversibly going to xm. This is a diluted reaction network, so as to say, because all the reactions have a single reactant or they're like it follows the three criteria that was there in the previous slide. And then we define something called a split graph. Split graph is a species-species network for a diluted reaction network in its essence. And why it's called split graph is because all the reactions are either one-to-one or one-to-many. All the one-to-one reactions directly correspond to like forward and backward edges. For example, xk reversibly going to xm is a pair of edges. And the reactions which are one-to-many get split into two edges, xi going to xj and xi going to xk, which are these two edges. And the two reversible pairs are reversibly there. So it's a directed graph made up of species of the network, and the edges denote if there is a reaction going from node I to node j. Further, for a slit graph, we can zoom out, so as to say, a generalization into a class graph. So all the strongly connected components of a split graph are denoted as classes. So here you'll see that xi and xl, they are strongly connected because there's a node to go to xl and then come back. In this case, this will be a class. So the class Ci is just the nodes xi and xl. And similarly, the class Ck is xk and xm, and the class Cj is the single node xj. So these classes, inside the class, all the nodes will be strongly connected. There will be a path to go from any node to any node. But outside these classes, they will necessarily be not strongly connected because if there were another node in Ck which is strongly connected to Ci, then it would be included in that class. So it's the maximal set of the strongly connected components. And then one thing you can note is that it's a directed acyclic graph. So it will be a directed tree or a directed forest, depending on the connectivity of the original network. So given this structure of it being a directed tree or forest, we have a notation of minimal classes. What we mean by minimal classes is because the directed tree structure gives a directionality to the class graph, there is upstream and downstream. Upstream is any class which leads an edge into this class, and downstream will be any class which the class gives. So CK is downstream from CI, and CI is upstream from both CK and CJ. And we say a class is minimal if there is no other class which is upstream from that class. So in this example, the only minimal class is CI because there's no upstream class from CI. And mathematically, the condition is that there is no split reaction in the system with one species in CI and another species which is out of CI, which would lead to an incoming edge into this class. So why we define these is because in a paper by Jeremy and Philip in 2022, they defined a property called the top property for autocatalysis. And what this property implies is that if you have a diluted reaction network and it satisfies this property, then it will be dynamically autocatalytic. And what this property is all the minimal classes of the graph contain at least one one-to-many reaction internally. So what this means is, for example, this Ci is the minimal class. The species Ci contains is Xi and Xl. And if we go back here, we see Xi and Xl are not involved in any one-to-many reaction. So this reaction network does not satisfy in this way. But if there was a one-to-many reaction and they are also strongly connected, so the property that makes them belong to the same class, and then it happens that that class is also the minimal one, then that network will be satisfying the top property. And in the paper, they proved that this top property is necessary and sufficient to say that the system will be dynamically autocatalytic. There will be an Lyapunov exponent, which will help the system grow exponentially from this dilute regime to anything higher. So in this paper, what we did was we did an analysis of the course based on these conditions of the top property. So there's the two differences that I mentioned from the previous analysis, of course, in the stoichiometrical sense, is that there are irreversible reactions and the stoichiometry is restricted. So how this analysis proceeds is the proof is in the appendix of the paper because it's a lengthy one, but it's graph theoretic. So we start with a single cycle and then we apply the conditions that it should satisfy the top property. And then we go through eliminating other possibilities. So for a single cycle, we get only two different types. Is either this type 1, which will somewhere in the middle have a doubling reaction, x going to 2x or x going to nx. There can be a type 2 with any number of back branches. So it's also a cycle. By cycle, I mean a sequence of species going x1, going to x2, going to x3, blah, 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 till xn. And then there's a reaction going from xn back to x1. So in type 1, there will be a cycle like this with one of those reactions, xi going to 2 xi plus 1 or nxi plus 1. And for type 2, there will be a back branch. By this, there will be an xi giving xi plus 1 plus xj, and j can be somewhere else on the cycle. So this is, all of these are strongly connected classes by themselves because there's a way to go around the cycle and come back to the original species. In type 1, the one-to-many reaction is the doubling or multiplicating reaction. In type 2, the one-to-many reaction is this back branch that happens. And then we show that there's no other minimal structure which can satisfy top except these two for a single cycle. And then we move on to the double cycle case where there are two cycles which are intersecting. And we again go through the procedure to see how can we have this satisfy top property. And then we find there are three different ways to do it. Then type 3, type 4, and type 5 appear with type 3 having one-to-many reaction, type 4 having two, type 5 having three. And then we show that it's not possible to go beyond two intersecting cycles and still have this minimality and top satisfied. So at the end, we get that if we look at it from the perspective of a diluted core satisfying the top property, we again get five different cores, which are almost exactly the same as the five cores that we get in the stoichiometric sense, but it's under a different setting with irreversible reactions and different stoichiometric constraints. So given these cores, then we moved on to the second part of the analysis of the paper, which was the uniqueness of the stationary state of these cores. So the first step is to notice that for these cores with irreversible reactions, there is no stationary state. It is a system which will always keep growing, which is by the definition of the dynamic autocatalysis. This will just keep increasing its concentration infinitely, and it'll just keep growing by the irreversibility. But the fact that it will keep growing is in contention with the assumption of the diluted regime, because at some point the system will start going out of the diluted regime and the irreversibility of the one-to-many reactions will start breaking. So that's why the first step we did was to have the reversible extension of the networks. What this means is we take a look at all the reactions in the network, and any irreversible reaction we make reversible. Like we add a back edge to that reaction. And then from now on, we will refer to diluted autocatalytic cores as reversible extension of the five cores that you see here. So all the one-to-many reactions, specifically these reactions which are doubling, they are made reversible. All the other reactions are already one-to-one, so they can be reversible, irreversible, it doesn't matter. And then this kind of a structure is called the diluted autocatalytic core. One thing we can note here is that once we have this reversible extension, then we are back into being a subset of the stoichiometric course, because now we have reversible reactions and we have the stoichiometry of each reaction. So for now, there is no degradation or inflow into the system. So it is an exact subset of the stoichiometric course. And in the previous paper, they proved that for the stoichiometric course, the stoichiometric matrix is invertible. So this gives us condition that all the stationary states we find here will also be equilibrium states, because as j is equal to 0 would imply that j is equal to 0, because the stoichiometric matrix can be taken to the other side. So given these, then we went on to examine what are the stationary states of these reversible extensions. So these extensions will give an idea of which direction the system is growing in. So there's growth, of course, but once the system grows enough, there will be the concentrations will be enough that the reverse reactions of the one-to-many reactions come into play, and they go towards a specific stationary state, which can be one or many or something, which is the point of the investigation. And that would imply that even in the dilute regime, the growth of the system was towards these states. It looked as a Lyapunov exponential growth, but it was actually towards this stationary state. So, for keeping into the time constraint, I will not go too deep into the deficiency theory, but it was defined by Hahn and Feinberg separately in different places. And a deficiency index is defined as the number of complexes minus the number of linkage classes minus the rank of the stoichiometric matrix. Complexes means the species which appear together either as a reactant or a product. So if I have A plus B giving C, then A plus B is one complex, C is one complex, and I can have a separate reaction A giving B, then A and B are also complexes. So this number is the number of complexes that are there. Linkage classes are the connected components of the split graph, so as to say. So link is the number of such linkage classes that exist and the rank of the stoichiometric matrix. And this gives an index which is called the deficiency index. And according to deficiency zero theory, if I have a weakly reversible network with a deficiency index of 0, then it will always admit a unique positive stationary state. Weakly reversible are networks which in each connected component, they are strongly connected. And for our cores, which are just single connected components and also strongly connected, they are always weakly reversible. And we show that all of the cores, all of the five type of cores have a deficiency index of 0. So this I display here as an example for type 2 with any number of back branches. If I assume that this L index is specific for type 2, it defines how many back branches there are in the cycle. So if L equal to 1 means there's only one back branch, this I1 to sigma 1, and the others are not there. Then the set of complexes are these. There's only one doubling reaction, so there's only one double complex and all the individual species, and there's only a single linkage class. So the efficiency index is 0 because the complexes are one more than the rank of the stoichiometric matrix, and the linkage classes satisfy that and bring the efficiency back to 0. If L is equal to 2, then we have two back branches. Then the complexes increase by 1, the linkage classes also increase by 1, and the efficiency does not change because these terms cancel out. These are the two linkage classes that you would see if L equal to 2. And this also happens if we keep increasing L. L goes to 3, we get 3 linkage classes and one extra complex, and then it also cancels out. And this kind of structure repeats through all 5 types of cores. So at the end, we can get that all the 5 cores have always the deficiency of 0. And this, by the deficiency 0 theorem, gives us the fact that it admits a unique positive stationary state. Further from this, there's a global attractor conjecture, which has not been proved yet, which says that for a weakly reversible deficiency zero system, the unique stationary state is also a global attractor. But for our case of the 5 cores, we can prove this global attractor behavior because we have a lemma that for any of the cores, there cannot be a stationary state with some concentration 0 but not all 0. That means there cannot be a stationary state which is on the boundary but not exactly at the origin. Any stationary state with any concentration 0 will have all the concentrations as 0. That's the only state which is possible. And near 0, if we take a concentration vector near 0, we can show by calculation that the overall concentration of the system strictly increases. So this means that for this system, there is one stationary state. 0 is repulsing, so any concentration near 0 goes away from 0, and it's not possible to go to any other boundary. So these two conditions are enough to say that the system will be persistent. It will not go to the boundary or go out to 0. And since there's only one unique stationary state, it will be the attractor throughout the system because deficiency 0 theory also gives that it's asymptotically stable. So this is the only stable state, and all the trajectories will end up in this stable state. So this gives the global attractor behavior for the 5 cores. One thing to note is that the next step, in the next step, is that we want to also investigate what happens when there is degradation in the system. So these cores will grow, but as the concentration reaches a certain limit, there will be other reactions which are outer system reactions, which will involve an outgoing edge from the network, which will take species concentration out of it. And we want to see if the autocatalytic cores still have the unique stationary state, if it's still going or it just collapses. So for this, we cannot use the deficiency zero theorem because when we investigate with degradation, most of the networks do not have a deficiency. All of the networks don't have a deficiency of 0. There's only type 1, 3, and 2 with one back branch that have a deficiency of 1, and we can apply deficiency 1 theorem. But for type 4, 5, and 2 with any more back branches, there's no existing method to analyze it. And this kind of structure we also try to see in previous papers, which involve adding degradation to systems and all these things. But it does not exactly fit the criteria. And a lot of times when the degradation rates are added, inflow rates are also added. But we wanted to investigate only the degradation rates because we are trying to see autocatalysis as something that helps system grow. Adding inflow to it is like a side way, it's an auxiliary method of growth. But here we want to purely see it as autocatalysis trying to grow the system versus degradation trying to reduce the system. And one very obvious lemma that we can start with is that when you have a high degradation, then there is no positive stationary state. And there's a bound Km. It's in this form because it's in this form in the paper. You get one term K from the kinetic constants. So you fix a kinetic constant. And then you get one term from the kinetic constant, one term from the stoichiometry of the structure of the system. And then you get that if all the degradation rates are bigger than this number Km, then there is no positive stationary state. The only stationary state is one at the origin. So given this how we proceeded through the investigation. I will give a rough sketch of the proof. In the paper, it's much more in the it has all the technical details, but I'll give the idea of how we proved it. Is that this is where what we have. So when there is no degradation, it's the deficiency of your system. It will have one state at the origin and one attracting state in the bulk. It's the positive state. For simplicity, I just put it as two dimension, but it's of course it's n dimension based on the number of species. And then for a certain high degradation, if you go beyond a certain limit, then there is no positive stationary state. There's only the zero stationary state. So how we prove is that we assume that there is some degradation set which will give us two positive stationary states in the bulk. And then because of this, it's possible to extrapolate between these sets. So we take the degradation as a vector which is alpha times ax, where alpha is a parameter we can manipulate. And then when alpha is equal to 0, we're in this setting, we have one positive stationary state. When alpha is large, somewhere larger than km divided by the smallest ax, then we are in this setting where there's no bulk. And when alpha is exactly equal to 1, for this case, then we have two bulk stationary states. So this is the assumption that we will prove by contradiction that it cannot be satisfied. Then one lemma that is used in this proof is that there is no degenerate non-zero stationary states for G prime for any choice of parameters. G prime, remember, is the graph with the degradation rates, which are strictly positive degradation rates, which will be called G prime. So for G prime, for any choice of parameters, if there is a positive degradation rate, there is no degenerate non-zero stationary state. So what this means is in this bulk region, it's not possible for during this extrapolation of the degradation rates, changing alpha, it's not possible for these two states to collapse into each other. It's also not possible that starting from here, at some point in this manipulation of alpha, from one state, it's split into two states. So we are blocking this phenomena from happening in the bulk. And another point is that from the lemma, we remember that the stationary states are not possible to exist on the boundary. So there's this red border near, which is exactly at the boundary. So these states are not allowed to collapse onto the boundary itself. Then how the theorem goes is how we investigate where these states can go. Assuming this is true, that there is two states at some degradation, where can they end up in to satisfy these two endpoints of the manipulation? So another lemma that we use is that the Jacobian determinant of the equations at the zero state is zero for exactly one value of alpha greater than zero. So given these two things, that it cannot collapse into itself in the bulk and it cannot go to boundary, the only place for these manipulations to go is going to the origin, the completely zero state. So we show that this state at zero, as we increase degradation from zero to some higher number, it can give a determinant of zero for exactly one value of this alpha, manipulating from zero to any high number. So how this helps us is that it says that this origin will have a degeneracy, which is given, it will have one degeneracy, but it will have it at exactly one value of alpha. This combined with the previous lemmas is enough to say that this kind of case cannot happen, because for this to happen, first of all, there must be one degeneracy at zero which gives rise to the extra state, and then there will be a degeneracy at zero which takes away these two states at some point here. So these two are incompatible with the fact that it can only happen at one point. And the bulk stationary state is also non-degenerate by the deficiency theorem, and also we can prove it using the structure of the network and child selections that they are in Nicola's paper, that this state is also non-degenerate at the zero degradation. So given all these tools together, we can see that interpolating between these two, it's not possible in the middle to get a state where there were two stationary states. So here we're not even talking about the stability, we're just talking about the existence of two stationary states. So we why there's a so we prove this to be true for all the types, except for type 2 with L greater than 2. The problem with L greater than 2 is because this step, that there is no degenerate non-stationary states for G prime finite choice of parameters. This is done by taking each type specifically and then assuming that there is a degenerate state in the bulk, and then showing that there are incompatible inequalities which happen if you assume this, and then which disproves that this kind of condition can occur. But for type 2 greater than L greater than 2, the equations become too complicated. I'm sure it's a possible generalization of the future where we can have a general method to prove that this lemma is true for all the cores. But for now, we have these for all the cores up until two back branches until type 5. So this gives that all the cores, apart from these, with strictly non-zero degradation, can have at most one positive stationary state. So this means that all these cores, when you add, even if you add degradation, they cannot have a complicated structure where there are multiple positive stationary states and the trajectories are going in a complicated way. It will always be either growing towards the one stationary state or not growing at all. It will require it will require an interaction of multiple different kind of feedback phenomena and multiple cores to actually have more complicated behavior, which is one short example I'll go through quickly because I see I'm out of time. This is an example where we have a type 1 core. So X3 goes to X4 and X4 goes to 2X3. This is a type 1 core. It's coupled with a split reaction, X1 going to X2 plus X3. And there are some inflows and outflows. The outflows are the degradations, but the inflows can also be modeled as an inflow coming from a different autocatalytic motif. So you have an autocatalytic motif with some degradation, and that degradation is going into X1. Just there. And in this kind of system, it's possible to get three, and I'm sure there will be examples where it's possible to get even more stationary states. One is stable, other unstable. Stability is another point which we can develop on later on in later works. But this means that for kind of more complicated behavior with multiple stationary states, multiple stable states, you will need interaction of multiple different cores. A single core itself, growing from a diluted phase, will always grow only towards a single point. And that was kind of the essence of the discussion. I'll stop there and thank you for your time and attention.